Okay, may I continue? Okay. Okay, let's hope it works. I mean, it claims it's recording, I think, right? That is good. So, okay, good. Okay, so today I want to start talking about the algorithms. So what can we do to actually solve either of these classes of games? So to start things, let us consider only the one-player version. Okay, so we will say that we have only one player, and on the slides I took the maximizer. Okay, so let us start with the discounted games. This is always a bit easier to analyze. So, so we have a one-player discounted game. So we have a maximizer who wants to maximize this kind of discounted reward from their payoffs, and by the theorem, by the Shapley theorem, right? In this one-player case, the optimal policy is, well, the optimal strategy is a policy, right? So it's a very simple function that, given the state, it tells you where should you go, and this should maximize the payoff. And we know that the value is characterized by the fixed point equations, but this time only with one player. So instead of having the equations containing both max and mean, I only have the max. Okay. So now we will exploit the fact that we only have the max. Okay. So since we only have the max, right? So xi is supposed to be the maximum. Well, when xi is the value. So the value is supposed to be the maximum of expression to this form, right? So in particular, it's supposed to be greater than this. Okay. So this kind of constraints, well, if we fix the discount factor, then these are linear constraints in X. So they define a polytope, or polyhedron rather. So we have here a polyhedron. And now we claim that if we look at this polyhedron and we minimize the sum of xi's on this polyhedron, then we get the value. Okay, so you are the maximizer. So you want to minimize a function on the polyhedron, and that will give you the value. So that's the theorem that is written on this slide.
So you're minimizing the sum of the values of each.
No, so this polyhedron here, so first observation, this polyhedron contains the value as one of its points, right? Because the value satisfies lambda I equals to max blah blah. So in particular, it satisfies lambda I greater than blah blah. So the value is a point inside this polyhedron. Okay, but now I claim that if I minimize the sum of xi's on this polyhedron, then this is exactly the value. Okay. So the only thing I need to show is that if I take any point inside this polyhedron, then this sum is higher than the corresponding sum for the value. Okay. So let us look at the proof. So if I take any point in this polyhedron, then, well, by definition, it satisfies x greater than the Shapley operator at x. This is just the definition of this polyhedron. Okay. Right, but this operator is monotone. So if I add f on both sides, the inequality is true. So now we iterate. So x greater than f of x, f of x greater than f2 of x, etc., right? So we get this. X greater than f, greater than f2, greater than blah, 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 greater than fn. Right? But this fn is a contraction that goes to the value. So we got that any point that is inside this polyhedron satisfies this inequality. So on every coordinate is higher than the value. So if you minimize the sum of coordinates, you will get the value. Is this fine? Yes.
And the max is the smallest value that's bigger than the maximum bunch of values is the smallest value that's bigger than all of them. That's all that's happening.
Yeah, exactly. Right, but the important bit here is, well, okay, we are using the fact that this is only one player, right? Because because for two players, we can of course also take a polyhedron, right? With just xi greater, xi smaller. It's a polyhedron. It contains the value, but this value point is somewhere inside, right? It's not a nice. It's not a nice point on the boundary that achieves subminimum, right? So it is somewhere there, but finding it is more complicated. But in one player case, it's nice because this point is actually, since it's unique, it should be a vertex, right? So it's a unique solution of this thing, so it has to be a vertex. Right, good. Okay, great. So we see that the one-player version of this discounted mean-payoff game, reduces to linear program, right?
Can you just go over once why x is larger than, when you say x is greater than f of x, you mean x is a vector, you're saying anti-y is.
Yes, anti-y it's greater. And it's just this range. Right? It is greater than every single guy, so it is greater and particular than the maximum of them. Right? So in f of x, you have the maximum, that's right. So this implies that this is greater than the maximum. Okay, so we see that this is linear programming, and we know that linear programming can be solved in polynomial time, right? So we have polynomial time algorithm for the one-player problem. Great. However, we can do a little bit better. So we can see that this program here has a very peculiar form. So this program, as you can see, in every inequality, uses only two variables, xi and xj, right? And there is a theorem of Megiddo saying that if you have a linear program that has two variables per inequality, then you can solve it in strong polynomial time. Okay? So if you apply a general algorithm for linear programming, then the complexity would depend on the bit size. So it would depend of the, the number of bits that you need to encode the discount factor. But by this theorem, you can do this in complexity that does not depend on the number of bits that encode the discount factor. Okay, so this is an improvement that you can do it in strong polynomial time. And, so this is a general theorem, and there is a lot of papers, trying to improve this for the linear programs with two variables per inequality. But there are also people who try to improve this for these peculiar programs. And the current best is O of Mn. So this is the number of vertices, this is the number of edges. Right? So in this time, you can solve a one-player discounted deterministic game. Very nice. Okay, so what happens in the mean-payoff case? So in the mean-payoff case, we saw that one-player mean-payoff case is basically just finding a cycle with the highest mean value, right? So you find a cycle with the highest mean value, and you want to reach this cycle. That's basically one-player mean-payoff game. And there is a theorem of Karp from 78 who asks himself exactly this question: how can I find the cycle of maximal or minimal weight? And he said, well, okay, I have an algorithm of Mn complexity, right? And if you can find the cycle, you can also find the policy in the very same complexity. Okay, so in both cases, we can do this in O of Mn. And, nobody has figured out if you can do this any faster since 78. So maybe you cannot. Okay, good. So this was the one-player case. So in one-player case, it's Mn. Okay, so the second kind of algorithm. So now we move to the two-player case. So let me start by discussing the simplest algorithm imaginable. We have seen the characterization of the value, right? And this characterization, well, just suggests you the value iteration algorithm. So what is the value iteration algorithm? Again, let us start with the discounted case. So in the discounted case, we saw that if we iterate fn of 0, we get to the value, right? And we know that this operator is a contraction with a contraction rate gamma. So when I do this n times, when I iterate this feed n times, I get gamma to the n, right? And just by saying that, okay, fn0 minus gamma is fn0 minus f of gamma, lambda, minus f of lambda, because lambda is a fixed point. So this is smaller than gamma times the same thing. And you repeat this thing, and you get gamma to the n times the supremum number of lambda. We know that this is bounded by the highest payoff. So this is gamma to the n times w. Wonderful. Okay, so now also recall that if we have discount factor p over q, then the denominators of this thingy of this value are at most this number, right? That was one of the lemmas on some previous slides. We can bound the denominators of the value. So this gives you immediately an algorithm, right? So you just apply these operators for this many times. Okay, and by doing this, you get very, very close to the value. Okay, so now if we want exact to be exact, you have to do some rounding. Okay. Or not.
The number of iterations should depend on W, not on to get epsilon. What are you trying to get? You're trying to get an epsilon approximation? I think it's 1 by 2.
Yeah,
Approximation.
I think so. I want to do an epsilon approximation, but what I want to do, I want this thing to be my epsilon, right?
Got it.
It's one over this thing or something like this. This is my epsilon. So I already put the epsilon. So because I want the exact number, right? So I put the epsilon that is enough for me to do rounding and get the exact value. Okay, this is what I wrote on this slide.
What is this rounding procedure have a reference? Isn't it this?
Well, because it's maybe not so obvious. Because what do you want to do?
So you just apply the same log of W times.
Yes. You apply the thing with this many times. And what happens then?
That's
Yes, that's enough. So you get some rational number, because when you apply this operator, you only get rational numbers, right? So you get some vector of rational numbers. And you are guaranteed that you are very close to the value. But how do you go from very close to exact? You have to do some rounding, right?
No, the denominator is not n.
It's at most. But so the reference is because I say like I like to do it like this. I say, okay, so the denominators are at most m. So, but if you have two rational numbers with denominators at most m, then there are at most 1 over m square apart. At least 1 over m square apart, right? So now by doing this sufficiently many times, I am less than 1 over 2m square from the actual real number that I searched, right? So now I take my approximation and I look at the interval of this length 1 over 2m square, right? And I want to find the only rational number with denominator bounded by m in this interval. And this is precisely what's done here. So
you're iterating this a polynomial number.
No. Okay, here is the thing. Here is the thing. Okay. Yeah, but that's written on the next slide. That's written on the next slide. So that's beautiful, right? That's beautiful. But there is a small problem. So imagine that your discount factor is this number. So you need k bits to store this number, but this thing is 2 to the k.
Ah, sure. Yeah.
Okay. So this is not a polynomial time algorithm, right?
But it's only one.
Okay, so it's not a polynomial time algorithm because this thing requires, this thing is exponential, the number of bits.
When I saw what was gamma,
Yeah, it's log of gamma.
1/1.
Exactly. It is log of gamma, but 1/log of gamma is much bigger than, well, than what you have. But you know, if you fix the discount rate, then it becomes polynomial, right?
In fact, if this time rate is only polynomial, it's polynomially bound, inverse polynomial away from one is still. Right, so if it's 1 minus 1 over poly n, it's still fine.
Okay, right. Good. So we have the first algorithm, right? So it's like a pseudo polynomial in the discount rate. So it's the trivial algorithm suggested by the proof of the theorem, but unfortunately not polynomial. Okay, good. So this is value iteration in the discounted case. And we can also do value iteration in the mean payoff case, right? Because we already also saw this estimate. So this is exactly the estimate that we used to prove that this iterative process converges. Like if you recall the proof from yesterday, this is exactly one of the steps that I used to prove that this converges, but this already gives you basically the algorithm, right? And the same. You just compute this iterative thing, divide by n for this many steps. And here it is a little bit even easier because now lambda has denominators at most n. This is just the length of the cycle. So it's at most n. So you do this for this many operations, and you use a rounding procedure to retrieve the exact lambda. Okay.
In the previous one for discounted gains, the dependency on W was logarithmic, right?
Yes, then the dependence of W was logarithmic, exactly. But here the dependence of W is not logarithmic. So again, this is not a polynomial time algorithm because you need to log W bits to store the payoffs, but this is in W. So this is a pseudo polynomial, right? Okay. And here you see that each iteration has cost like of the number of edges. So you get the theorem that you can find the value of a mean payoff game in this complexity, right? So here, okay, I didn't mention this on the previous slide, but in the previous case, for discounted games, we saw that finding value and optimal policies is exactly the same because from value, you get optimal policies just by looking at the fixed point equations. Okay. So it's trivial from the value to find optimal policies. Now here it is less trivial because if I just give you the value by this algorithm, then finding optimal policies is still not so clear. But so there is a trivial thing that you can do. A trivial thing, if you have such an algorithm, is to say, okay, so I will run my algorithm, I get the value, and then I take an edge of my graph and I remove it. And I rerun my algorithm and check if the value changed. If the value didn't change, great. I removed one edge and I will remove a second edge, right? And if the value changed, oh no, I put the edge back and I remove another one. Okay?
Well, you put the edge back.
I put the edge back and remove the other edges of the node because now I know that this edge has to be in an optimal policy, right? Okay, so if I have an algorithm that gives me a value, I can call it polynomially many times and I will get optimal policies. Of course, it's, you know, it increases m by one stage, right? Because for every edge I run the algorithm, so I would have m squared here, I guess. And you know, we can do some things that are maybe maybe more clever than this brutal thing. And you know, people thought about it, and for the, you know, in the 20 years since this paper, we got this complexity. And it's both for the value and optimal policies. So, you know.
You can get n squared and log n just by doing binary search on the edges of each vertex.
Yes. I think this is what they do. Something like this. There are some logarithms that are here, right? But okay. So, okay, but so the current best for finding value and optimal policies is this. In terms, yeah.
So, you are doing this F to n, as I mentioned. So then you're doing this, you're going to find F to the n to n plus one.
Yeah.
Imagine trying to compute F to the n from F to the n.
Oh, yes. Of course, yes, that would be a great thing. Yes, exactly. If you could magically from Fn go to F to n, that would be immediately polynomial. But the problem is that you cannot do some kind of repeated squaring or however it's called here, right? Yes, it's but because it's it's with max and with mean, right? You run into the same kind of, if you do tropical algebra with max plus and mean plus and stuff like this, you run into the same problem when you try to how to say it, when you try to like multiply tropical matrices or find powers of tropical matrices. If I give you like a tropical matrix and you want to tropically raise it to a power, then you cannot do that. Then there is no like repeated squaring that we know of. And and this problem that the fact that we don't have it is like equivalent to all of this all pairs shortest path fine grade complexity questions. So this is like raising tropical matrix to the power is exactly this is all pairs shortest path question.
So you could go from like n cubed to
squared
again if you could do that.
Yeah, but then so for all pairs shortest path, the open questions, can you do this in n to the 3 minus epsilon?
If you square a tropical matrix, that's not the output is not tropical. That you can apply a tropical matrix on something multiple times. But
so you can define a matrix multiplication like in the usual algebra, right? So there's the same formula, you just replace multiplication by addition and addition by maximization, right? So and you take a matrix and you want to compute the nth power of this matrix, right? So normally you just square the matrix in the usual thing.
The adjacency matrix of the graph.
Yeah.
The eighth power of this matrix is the shortest path between I and J that goes through at most payload distance.
Yeah, exactly.
I understand.
Yes, you're right. Yeah, so you take the weights of your graph in your adjacency matrix and you're tropically powering it is like computing the shortest path. Yeah.
So if you could do repeated squaring, you would do it in n squared log n. Matrix, the matrix to the n would cost you an n by n matrix to the power n, which in the case of a graph will just give you the shortest path. If you take the adjacency matrix of a graph and you power it to the n in the tropical ring, it just gives you the matrix of shortest paths between any two vertices. And if you keep powering it on gas times, because you take at most n times to reach any. But if you could do repeated squaring, this would cost you like, let's say, n squared log n. To get the matrix to the power n, so you could solve all pairs of spans inside and square it again, which I guess is this APSP.
Yeah,
They can't do that.
Yes. And it's like, you can even prove it's like even only if like finding the power of a tropical matrix has exactly the same complexity
How
of
much
type.
underground is that APSP goes to?
Okay, so repeated squaring tropically is hard. It's hard, yeah. So in particular, yeah, in this operator, it would be great if you could repeatedly square it, but it's yeah, we don't know how to do it in any really faster way. Okay, so these are the two very basic algorithms suggested by the theorems. So let me also present you a third class of algorithms called the policy iteration algorithms. And to be honest, when I say we have linear programming in one player case, value iteration in the two player case, and policy iteration in the two player case, well, I am not covering all possible algorithms, but the vast majority of it, right? There is really not like that much variety, right? There is like the so-called GKK algorithm, which is different, right? But the others are like some variations of let us try to do policy iteration like this, or let us try to do value iteration using something, you know, but these are like the two main ideas. Okay, so what is the policy iteration? So we saw that, well, a game has an optimal policy. So the idea of policy iteration is as follows. So let us take some policy of one of the players. Okay, so since we can solve one player case, we can check if a given policy is optimal. So you just take a policy, you find the optimal
Response to the
yeah, you find the optimal response. Yeah, okay, so let us focus on the discounted case first, right? So in discounted cases, you take a policy, you find the value, and you check if the value is the same as the value of your original problem. Okay. And that's
Take it both. Wait, what are you trying to solve? You check if the policy is up.
yes, you can check if the policy is optimal. So in the discounted case, it's very easy, right? You just take a policy, you compute the value given this policy, and you check if this is the value of the entire game. End of story. Okay. In the mean-payoff game, what will you do? Okay, in the mean-payoff game, it's maybe a little bit more complicated, right? To check if a given policy is optimal, because if you find an optimal response, and then you try to find an optimal response to the optimal response, are you guaranteed that it's okay? Right. Yeah, so this is what we will actually do in this case, okay, but
There's policies that are optimal.
but there are not black hole optimal, so you know, checking like this.
So the black hole optimal policy is not the only optimal policy.
Yeah,
There's optimal policies that aren't even.
yeah, not even used by AWS, yeah. Yeah, so okay, so let us start with the discounted game, okay? That's much easier. It's easier, much easier also for the algorithm, actually. So in the discounted game, we saw that, okay, if I give you a policy, it's very easy to check if it's optimal. You just find the value, check if the value satisfies the equation, and okay, good. So can we use this to actually improve the policy, find a policy that is better than the current policy? And the answer is yes. And this is the idea that is written on this slide. Okay, so what we want to do is we want to make a local improvement to my policy. So I have my current policy, I check, well, not optimal, and then I want to improve it. by switching some edges. Okay. So the idea is as follows. Okay, so I take a policy, I compute the value of the one player game, right? So if sigma is not optimal, then the fixed point equations are not satisfied. So what does it mean? Well, if I am the maximizer, it means that I have at least one edge. There's at least one edge that satisfies this, right? So lambda I is not the maximum. In other words, there exists J such that this is greater.
Lambda to the sigma is the value for one player game where max uses sigma.
Uses sigma, yes.
So min has a response. So it computes the best value for the min player given the strategy.
Yes.
Now, if sigma were an optimal strategy, then the player will do better, the min will do better, so the strategy would obey these equations.
Yes. Exactly. This would obey the equations. So if it's not optimal, then it doesn't obey the equations.
Okay.
So you find an edge like this.
To compute the response, this gives you some value, and the sigma, has to be an edge of max, which doesn't obey this equation.
Okay.
And so you, okay,
And okay, and now the intuition is, so what is the intuition, right? So imagine that I do the following thing. I go from I to J.
this for this,
Yeah, for this kind of thing. So imagine I do the following thing. I go from I to J, and then I use sigma. Okay, so it's not a policy anymore. I described the strategy, right? So I look at this, I go from I to J, and then I use sigma. So what is my payoff when I do something like this? Well, it's exactly this. Right? So by doing this kind of strategy that is not a policy, I guarantee myself something better. At vertex I, at least at vertex I, it seems so, right? So we will make a proof on the next slide, but that's the idea. That's the idea. If instead of doing what I'm doing at I switch to going to J, I should improve.
is also policy.
Yes. I will switch it to be a policy. But in my arguments, I can argue about more complicated strategies if I want.
What you just described is also policy.
Yeah, of course, yes. So that's the idea of the algorithm. So in the in the limbo of the policy iteration algorithm, we call such edges improving edges. So an edge ij
is J minus the sigma I.
yeah, because this is a fixed point of your operator, one player operator, so it satisfies lambda I sigma equals to 1 minus blah blah with sigma. So it cannot be sigma I.
It's because, in other words, because sigma lambda by sigma is just the value that max would get against the strategy found for min.
Yes.
Right? And if you started I, there would be 1 minus gamma Ri sigma y plus. Right? So if you started I, I know I can do that now, it's just following the sigma I.
Yeah.
So that would be lambda I, and now you're saying it works. So if I switch from sigma I, which is what the maximizing player is going to be doing, to J, I will get a little better.
Yes, so that's the idea.
Yeah.
You will get a little bit, right? So that gives you an idea for an algorithm. So you start with some policy. You compute this improving edges, which you can do. Choose some of them, maybe all, maybe not all. Some of them, switch to these edges, and repeat. Okay. So that's the whole idea of the algorithm. So now let us
the value does not decrease with any other.
Yeah, of course. Yeah, this is exactly the proof that is on the next slide by Hubbard. This is holds and is correct. Okay, so now this sigma hat will be the switched policy. So by definition, so this is the observation that one has to make that if I now look at the new operator at the old value, then by definition of my switched policy, this inequality is satisfied because these are the improving edges. Right, so lambda sigma I was smaller than 1 minus gamma Rij blah blah, but in my new policy, this is exactly the value of f sigma hat at this point. Okay. So by definition, we have this inequality. So it's new operator on the old point. Okay. But now the same thing as always applies. Iterate. Apply f with this new sigma hat. Apply. Right? You get this. Okay. So what is in the limit? Well, in the limit, you know that your new value is at least the old value on every coordinate. That's by application. But moreover, this is not a fixed point because we have this strict inequality. Right?
Improve it on coordinate, but also you don't get worse on that.
Yes, you don't get worse on any coordinate, and on at least one you improve strictly. Okay.
And intuitively, you don't get worse because you're always doing the same. Maybe you go here through this vertex again, but here you've improved. So everywhere else you do the same, right? And that's actually what is being proven in this.
Yeah, exactly. This is what is being.
When you iterate, you're saying like more and more steps. But
Yeah, exactly. Right. Yeah.
I always get something better. So when
Exactly right. So we improve. So at least one coordinate strictly, and on every coordinate we.
So you said by definition we have
This, yeah.
but the definition only can work for one of the coordinates.
Yes.
Was it for all?
no, only for one.
Yes.
So sigma hat is the strategy where on some of the vertices where you have an improvement, you switch the end.
Yes, but you keep all of the others, right?
All of the others.
You don't switch them. You only do the switches on the improving edges.
So on the ones you switch, you actually have a strict inequality.
And on the remaining, you have equality.
No, because they weren't. Right, that's not involved in that.
Okay. Yeah. So here actually you have strict inequalities and equalities. Well, this is always a good stuff. I have strict on the guys that you switched and equalities on the guys that you didn't. Okay. Well, so you strictly improve. So since you strictly improve and there is a finite number of policies, you will stop some point. And that's the proof that it works. Okay, good. So now, well, there are many questions that you can ask, right? So for instance, what happens if I have multiple possible switches? How should I switch? What is the best rule for switching? Well, what is the complexity of this algorithm? Right, there is a trivial bound on the complexity. Well, just the number of policies, right? You cannot run through, you can maybe run through all of them, but not more. So that gives us an exponential bound immediately. But can we do better? So there are all of these very interesting questions, and a lot of people study these questions. So there are many rules on how to choose which subset of improving edges you should choose. So Howard actually proposed the simplest and perhaps the most natural rule. Well, you have all of these improving edges, so just take all of them. But you know, sometimes at the vertex, you may have multiple improving edges. So which one do you choose? Well, you choose the one that gives you the most improvement, right? So you choose the one that gives you the max, and you do this for every vertex that can switch an edge. So this is known as the Howard's rule or as the greedy all switches rule. Okay? And this is considered to be like the most popular policy improvement rule. And actually, in many papers, when people say policy iteration, what they mean is policy iteration with this rule. But it's so common for them that they don't even specify that they think about this rule. They just say policy iteration. Okay, so this is most standard rule, and this is the most studied rule.
Something missing in this statement.
And there is a theorem.
Maybe it's silver
No.
or fixed now.
Yes. So there is a theorem that this policy iteration with this rule, has this property that if you fix the discount factor, then the number of iterations is actually polynomial. Okay, and the best bound that we have is this quantity. Okay. So with a fixed gamma, you do this many iterations at most. But again, this is only for fixed gamma. Well, the improvement, but also you see here that this doesn't depend on W, doesn't depend on the payoffs. Right, this bound. So it's like a combinatorial bound that only depends on this. Okay, so this is how we can solve against efficiently for the fixed discount factor. So that's one rule, but there is a second, a very important rule in the literature, because I told you that we can solve these games in randomized sub-exponential type. Okay, and this is like the best complexity that we managed to squeeze, like in the absolute sense, right? It's randomized sub-exponential, and this is achieved by this rule, policy iteration rule, called the random facet. So the random facet rule was proposed by people who do linear programming as a rule for pivoting in the linear programming. So this was proposed by Kalai and independently Mateusz Skomra and Welz. But actually Mateusz Skomra and Welz already realized that the rule is applicable not only to linear programming, but to the whole class of the so-called LP-type problems. And then people realized, it was in this paper by Hallman, that actually this mean-payoff or rather discounted games fall into this category. So you can just use the random facet rule and get sub-exponential time algorithm. So here is how the random facet rule operates, if you are interested in the detail. So the random facet rule operates as follows. So you take your initial policy. Okay, so it uses some edges, right? So now let us take all of the edges that your policy does not use. So that will be this vector pi. Okay, so you take this vector and you randomly permute it. So now you have a random permutation of the edges that you don't use. So among these edges, choose the first one that is an improving edge. Okay, and switch to this edge, right? So after the switch, you are using this edge, so you have to update your vector pi, right? So you have to remove this edge from the vector pi and put your old edge there, right? Because at each step you want in this vector to have the edges that you don't use. Okay, and then you take the initial part of this permutation and you re-permute it. Yes, so you take the edge, you remove it from the permutation, you add your old edge to the permutation, right? And then you take this initial part.
So I do have permutation. The first improving edge is in position L.
L, yes.
So now I replace what's in position L with my new edge. And then I permute again everything.
Everything up to index L. You re-permute everything up to index L. And continue.
So you're done with one iteration.
Yeah, that was one iteration. And now you have your new permutation. So you take the first edge that is improving for your new policy, and you repeat this process.
So we never care about anything after L, or it's the same order after L.
Yes, after L, you keep it. You keep it. You keep it.
Go through it.
Yeah, exactly. That's the whole point, right? That's the whole point. That maybe at some point, actually, the first improving edge will be the last one, and then you will repermute everything, right? That's the recursive procedure. So I wrote the non-recursive version, but the recursive version is that you fix one that you don't use, right? So the last one is the guy that you don't use, and then you use it only when you have to.
When you say one iteration, that actually starts from the sentence, take the first edge. Like everything
Yes,
before take the
yes.
first edge is not part of the iteration, it's just the initial step.
Uh,
Like you shouldn't
Yes.
on your second iteration do it on.
yeah, of course, yes. Exactly. So yeah, as your initialization step is you take a policy and randomly permute edges that are not there. So this is your initialization step. Okay. And after that, you start by saying, okay, let me take the first edge that is improving. Let me switch, update exchange the edges in the permutation, repermute the traffic, the initial part, find the first edge that is improving, switch, update the permutation, find the first edge that is improving, update the permutation, switch, update the permutation. Okay.
There's some kind of education provided.
Maybe they have some intuition for that. I checked I checked the easy part of the proof, because in the paper they say, okay, let us start with a situation which would translate to you have only two edges per vertex, right? So you have this kind of switch. And in this case, yeah, the proof is like, well, there is some, you look recursively what happens, and you say, well, let us divide the edges into this set and recursively say what happens, and the recursion on the exponential thingy, and you get some recurrence. But the recurrence is, let's say, known, at least appeared in some other places, and that it has some combinatorial interpretation, and it's known that when you solve it, you get a sub-exponential function. But then they say, okay, so what happens if I have more edges? Then we do this thing, and the recurrence is more complicated, and then half of the paper is studying this recurrence to prove that it's still sub-exponential. Okay. So in this first case, I guess one can maybe have some intuition as to why. In the other case, well, it so happens, and so the complexity is this: square root of n again in the exponent. There are some assumptions on which it works, but if you iterate with respect to player who controls more nodes, then the assumptions are satisfied. So the interesting thing is that this is independent of the discount factor, right? The number of iterations here in expectation is bounded by this quantity that is just square root of n again. But that's one thing. And the other thing that I wanted to say is that this is a very kind of singular rule, right? So you have all of these other rules, greedy, this random dancing, random edge, random something, Zadek rule, not Zadek rule. And there is like a whole plethora of rules, which you can randomize however you want. But still, this is the only one that has a sub-exponential. So there's like a big open question, for instance, for people who study these rules. Well, this uses a lot of randomness, right? You take random permutation and then you update this random permutation randomly at every step. So can you find a randomized rule that uses like little randomness? But it's an open question. Okay, but this gives you the current best bound on the complexity of these games. Okay, so now let me move to mean-payoff case. So mean-payoff case is, well, much more complicated than the discounted case because we don't have this operator, and all of weird stuff can happen. So the most natural thing to say in the mean-payoff case is that, okay, so I do the same as previous. I find the policy. I find the value of my policy. Good. So now if I can move to a neighbor that has greater value, then that's great, right? Again, intuitively, I just move there and I use my old strategy, I get better, right? So given a policy and the value, we say that the net is improving in this satisfies this, right? So my neighbor has a greater value than myself. Good. But unfortunately, this doesn't converge. So here you are a maximizer. So imagine that you start from this policy that goes from 1 to 1 and 2 to 2. So you get 0 and 0. So since you get 0 and 0, switching gives you nothing. You switch there, you get 0. You switch there, you get 0. I mean, according to this criterion. Sorry, according to this criterion, you don't have an improving edge. Because your neighbor has 0. You have 0, your neighbor has 0. Right? Right? This is 0, this is 0, so no improvement possible. But of course, this is not optimal, right? Because when you do this cycle, you get half. So this doesn't work. So now the question is, well, how do we make something that does work? And there are a few ideas that are summarized here. So the first thing says, well, we saw that we can just reduce the game to the discounted game, right? There was this Blackwell threshold, you apply the sufficiently high discount factor, and you get policies that are Blackwell optimal, so they are optimal. So you just apply this discount factor and run policy iteration for discounted game that works, that gives you optimal policies, and you are done. So this is the most trivial idea, but actually in our paper with Bruno, this is basically what we use, or a variant of this. Right? So the simplest idea, there is one variant of this that is maybe a little bit more complicated, but it's slightly different, however. So, you know, as this discount factor goes to 1, the set of improving edges will at some point stabilize. Okay? So you can follow this, say that your edge is improving if it's improving for all discount factors close to 1. And you can compute this set of edges. There is a procedure to compute it in polynomial time, maybe not fast, but in polynomial time. So if you now use these edges, you will, in a sense, follow the discounted game with extremely high discount factor. So it will also converge in the setting, but it seems that somehow people did it like it's there is a little bit about this in the literature, but maybe not that much. But so that's one idea that one can also have. There are people who studied the somehow restricted version. So instead of finding optimal policies, let us just find the policies that guarantee you the correct sign of the value, right? So you just want to find the states that are positive, has positive value, negative value, and 0 value, right? And we only care about policies that guarantee you that the value is positive if it can be positive. So it's not optimal, but at least it gives you the correct sign. So if we do that, then there is some other policy iteration method that you can do. And this problem, this kind of 0 partition problem, this is how people call it, is quite interesting for many people who do these games from the point of view of automata theory, because then they are interested in this kind of states of value positive, negative, and 0. So they came up with a bunch of other algorithms for this problem. And finally, the final idea is to use the so-called bias vectors. And this is the idea that I want to explain to you, because this introduces the notion of a bias. So what is a bias? So let me recall you that we said that the value of the discounted games can be developed into a power series near 1. Okay, and the first term of this power series is the value. Okay, so now I will look at the second term. Okay, and we will say that the second term is the Blackwell bias of this game. So that's the definition of the Blackwell bias, right? So in other words, you can define this as the series. Because this is coming from this, right? So in the series, you have the value, and the second guy will be called the Blackwell bias. Okay. And now we want to do the following thing. So given a policy, right, we can compute the value of the game, one-player game, and we also can compute the Blackwell bias of this one-player game. And this is some linear algebra. Okay, maybe it's not completely linear algebra, but this is the one. Okay. If you know, yeah. Okay. I didn't try to write down how to do it, but okay, let's trust me that you can just compute the Blackwell bias over one player game. Okay. So now
You want to take that or just approximation?
exactly. Exactly, yeah. So there is some linear program that will just do this for you. Okay, that's the thing. There is some linear program that will give you this Blackwell bias for one player, and since we are deterministic, it's probably much faster. But in the stochastic case, there is a linear program that will give you this. So in the deterministic, it has to be faster. But yeah, I forgot to check how to do this. Okay. So you complete both the value and the Blackwell bias. And now you modify the definition of improvement. So we will say that the net is improving if this pair is strictly higher than this pair in the lexicographic. So what do I mean by that? So if my neighbor has a higher value, then great. This is an improving edge. However, if my neighbor has the exact same value as I, then I also check what happens to the bias. And this is the criterion that you are using. So you are using the bias of the neighbor plus the payoff on the edge versus the bias, your local bias plus your local bias. Well, which in this case is exactly the same as the value of your neighbor. You only apply these two things. Okay, so this is the criterion. Okay, so it's not a clear criterion as to why it should work and
It's something like a gradient method.
yeah. Yes, so yes, it's interesting what exactly is the interpretation of this kind of improvement criterion, but it somehow takes into account like a second order information, right? So we are not only looking at the value, but also somehow at the second order of what happens, right? And there is this theorem that Blackwell proved in the one-player case. So if you use the one-player stochastic case, and he proved that if you choose this rule, this criterion as an improving criterion, then you will converge in the one-player case. So now let us look. So now we have an improving edge because one says, okay, so the value of my neighbor is the same as my value. So now, but now the Blackwell bias here is 0, the Blackwell bias here is 0. So now if I take the Blackwell bias plus this value, I get 1. And here I get 0 as my second coordinate vector, because it's 0 plus 0, and here I get 1 plus 0. So I will switch from 1 to 2. So now I go 1 goes to 2 and then we stay. So still the value is 0, and still the policy is not open. But now we are at this vertex, what happens? So my current value is 0. My neighbor's value is also 0. However, my second part of the vector is 0 because it's still 0 plus 0. But if I go here, then what I get? I get 0 plus the Blackwell bias here. But what is the Blackwell bias here? In this situation? Well, in this situation, the Blackwell bias is not 0 because the Blackwell bias comes from this last term, this term in the discounted game, right? So here in the discounted game, I get 1 minus gamma. So my Blackwell bias is 1. After the first switch, the Blackwell bias changed and it's now 1, 0. So now from this vertex, you want to switch to 1. And after 2 iterations, we go to this loop. And so we are optimal. Right? So it's a non-trivial thing that this actually converges, at least in the one-player case. Okay?
Can you go to the previous slide, please?
Sure.
In this, when you found an input, first you're comparing the values that makes sense to me. In the second part of the vector, Rij is the plot from the X. Okay. But you're comparing it with something which doesn't have anything about edges. So that's a bit. And should it be?
No.
J somewhere?
So, no, no.
So you compare the value of J and sigma I. Comparing the positive one plus the bias.
So I can tell you what is the interpretation of this. Well, this is the weird interpretation. But so imagine that you are playing a discounted game for a very high discount factor. Okay. So now your value at your state is this kind of develops into this series, and the value of your neighbor develops in the same series, right? So now, if you want to do the switch in the discounted version, you would compare these two series lexicographically. Okay, and now this rule tells you compare only the first two terms. These are exactly the first two terms that you get when you do the computation. So instead of comparing infinite number of terms, compare 2.
I just don't see why the second thing is.
Yeah, okay, but it's you know you would need to right because it's like applying the. I can maybe write it on a slide if you want. But I will stop this for a moment. Okay, so I can maybe write something, right? So we said that the switching criterion for the discounted case was this is smaller, right? J plus gamma. J gamma this? Okay, so now imagine that this gamma is very high. So both of these things can be developed into a series. So what I get here, I get my lambda j. This is okay. So this I get some kind of a C1I plus C2I1 minus gamma plus dot, right? Smaller than 1 minus gamma I by j plus gamma now we have C1J plus C2J1 minus gamma plus the determinant. All right? Okay, and now you have to put this together. So you have to develop this thing. So you say that this is 1 minus gamma Lij plus, and now you have gamma C1J plus gamma C2J 1 minus J, 1 minus gamma plus some higher order terms. But now look at what happens. Rij, so I want to develop it around 1. So I have to write gamma as 1 minus gamma. C1J plus, and here the same, I will do the same. C2J 1 minus gamma, right? Okay, so now I get what? J plus C1J. So yeah, so this is your first order term, right? So this is the term without 1 minus gamma. And now what contains 1 minus gamma? What contains? So we have minus C1J. And here you have plus C2J. And you have higher order terms. All right? Okay, so now that so you get C1J plus 1 minus gamma, and now you get Rij minus C1J plus C2J, right? Plus the dot. But now look. So this is the value of the mean payoff game at I. This is the value of the mean payoff game at J. So if this is higher, then the whole series is higher, asymptotic. But if these two are equal, then what does it mean for this to be asymptotically higher? It means that Rij minus the bias at J plus, sorry, minus the value at J plus the bias at J, right? So this is on my slide Rij minus value sigma at J plus bias at J. And this on my slide was the bias of sigma at I. Hopefully, I probably made a mistake on my slide, but okay. Okay, so now the second criteria that you should use is UI sigma smaller than Rij minus sigma J plus U J sigma, or in other words, sigma J plus U sigma smaller than Rij plus U J sigma, right? But this is the same as sigma I does this, right? Because you only apply this criterion when these two things are equal. So you can write this as like this or like this, that's the same number. And I hope that this is what I wrote on my slide. But that's the intuition. I made intuition, derivation of this. So this is the idea. You compare this asymptotically, but you only stop at the second term. Right. So I have here Rij plus U sigma J, and it should be higher than this thing. But now this, of course, yeah, this should be my preferred bias.
I switch it to sigma.
You got I, right?
On the way.
Yeah, I think here you should have indices I instead of sigma I in this thing.
So we want to say idea is improving from
Uh,
a previous policy.
I think that's the answer. And because this is the value that I am saying. So I should write it like this, but this should be the value that I plus the value of the bias I. That should be the bias of I. So the sigma that we use. Yeah. So, okay, I should have it this time. So that should be the bias of I. Okay, so there is the theorem by Blackwell that this will converge for some reason. Okay. So that will converge. And there is actually a conjecture about this method saying that, well, we think that this converges in polynomial time on one player deterministic problems equipped with the Gridiel switches rule. Okay. So, well, so that's kind of an interesting conjecture because, so you have one player deterministic game. So in other words, you want to find the cycle of highest mean, which we know how to do in polynomial time. You have a policy iteration algorithm, which simply takes your current set of edges and updates them to a new set of edges. And the update rule is, be not that complicated up to computing the bias, Blackwell bias. Okay, so yeah, so now I realize that I am, yes. So, but in the one player case, if you fix the policy, okay, then you just have a graph that has a paths and loops at the end, right? So computing the Blackwell bias of this thing is just linear time. There is like an explicit formula, which you can derive, okay? So in this case, computing this Blackwell bias is easy. So computing all of these improving switches is easy in the one player case. So you have this simple algorithm that will find you the max cycle of maximal weight. So you could think that, well, surely there is a proof that this converges in polynomial time that fits on one page. But we don't know. We don't have a proof. We don't know. We conjecture it. Okay. Now in the stochastic case, this is not true. In the stochastic case, this can take exponential time. Okay. So this is about this policy iteration role with the Blackwell bias. So there is an interesting kind of thing that I have never seen a proof that this rule, this with two terms only, converges in the two-player case. So I don't know if it actually does. So in the one-player case, yeah, it was proven by Blackwell, but does it converge in two-player case? I don't know. So I don't know if this does it, but there is another kind of a variant of this algorithm by Cochet-Tarasson-Gobert and Gunavardena. So they made an algorithm that also uses two vectors, value and the bias, but they use a little bit of a wider class of biases, so not only the Blackwell bias. And in their algorithm, they have some kind of degenerate iterations also. When you don't improve the policy, and you just say, well, my bias is wrong, so I will stay the same policy, but I will go from one bias to another bias, and somehow this going from bias to a bias allows the algorithm to eventually somehow break out from this policy and improve. So there are some degenerate iterations in the algorithm. But this can be done. Okay, so that brings me to my paper with Bruno about smooth analysis. So the problem of smooth analysis starts with the following observation. So so I told you about the algorithms for games, right? So let us implement them in random to see what happens. So we can, for instance, implement policy iteration. So this is a graph from Gobert and Bingrach, which implemented this method by Gobert and Tatarov, and co-authors with the bias vectors, okay, for mean-payoff games. So they run this policy iteration algorithm here on a complete directed bipartite graph with n edges, and here is the number of n. So it's like 1,000 by 1,000 edges, nodes, right? And you have all possible edges, and you pick weights, I think integer uniform in this. Okay, and you run the policy iteration algorithm, and you see how many iterations does your policy iteration take to complete the thing. So the red thing is the maximal number of iterations. So as you can see, I have 1,600 by 1,600, and the maximum number of iterations is like 40. While an average number of iterations is like 7. You see, 1,600 nodes in a complete bipartite graph, you normally converge in 7 iterations. Yeah, they all switch, yeah. Okay.
So when you say the ways of taking units only, you mean integer rates.
Integer. Okay. So this is interesting, right? So on the top of a slide, I tell you that policy iteration methods may require exponentially many steps or sub-exponentially many steps, and there is a whole group of people who find such examples. So it was initiated. Well, it's an old story because for linear programming, it goes back to the 60s by T and Minty and so on. But the modern era started with Friedman. And nowadays it's a whole domain where people find counterexamples to different policy iteration rules for simplex or for policy iteration but for games. So yeah, so in very carefully constructed examples, you can take exponentially many steps. But if you run it with random weights, then it becomes super easy. Like, it's not even linear in the number of nodes. It's less than that. So that begs the question, right? That begs the question, well, why? And can we prove it, right? Can we prove it? Can we prove formally that if I take my weights at random, then these games are easy to solve? Okay, so that somehow the hard instances are isolated, are very isolated. So when we take, sorry? Or yes, that the hard instances have like measure 0. I mean, we will do this in the sense of smooth analysis, which is even a little bit stronger. That will explain on the next slide of the techniques, right? So our contribution with Bruno is to say that the answer is yes. We can prove that games are easy in this randomized setting in the sense of smooth analysis. Okay, so let me tell you a few words about smooth analysis because I don't know if you know it. So smooth analysis was introduced by Spielmann and Tang to explain the real-world efficiency of the simplex method. So the simplex method, there is a similar story. So simplex method can take exponentially many steps in the worst case, but if you run it on real-world examples, it converges and usually linearly in the number of inequalities and the dimension. And people also tried to prove, well, why, or to try to study why it converges fast on this kind of random iterations. And Spielmann and Tang, let's say, introduced the framework that somehow explains this behavior. And they proved that yes, in this framework, there is a simplex rule that is fast. So here is the setting of the smooth analysis. So in the smooth analysis, we say the following thing. So let us fix an instance of your problem. That is maybe hard, okay? So for instance, for linear programming, you would fix a matrix and a vector. In our case, we will fix the weights, right? So you have some numerical data of your problem that is fixed, and it may be hard. And what do you do then? So you take this numerical data and you add some Gaussian noise to it. So you perturb your the numerical data of your problem, right? And you add this Gaussian noise with variance that is 1/5, right? So the higher phi is, the less noise you add. The lower phi is, the more noise you add. Okay. And now you have some algorithm like simplex method or policy iteration on some other algorithm. So now what you want to prove? You want to prove that your algorithm is fast when this parameter phi is small and your algorithm gets slower as this parameter increases. So this kind of interpolates between this very hard situation, because initially you fix something, it may be very hard. So you add noise, and the more noise you add, the easier the problem becomes. So what is the interpretation of this? Well, the interpretation that they give of this is that, okay, so my hard instance is like a singular point, but if I take it and just go randomly around it, suddenly everything around it is easy. So, and there is like a maybe hand-wavy real life interpretation saying that, in the real life, the programs, there is always some numerical noise and stuff like this, right? It's like floating point and the data is like a little bit truncated. So maybe this kind of explains the real world efficiency of a program, right? So that's the explanation. And they were able to prove that the simplex method equipped with the so-called shadow vertex pivoting rule stops within this number of iteration in expectations. Okay? Which means that, okay, indeed, if you add very little noise, this blows up. If you add a lot of noise, this stays bound. Okay, so there are these two things that one can study. One can study what happens in expectation, or one can study a little bit weaker version, which is what we actually do with Bruno, is to study what happens with high probability. Okay, so we will prove that with overwhelming probability the games are easy. Okay, so what happens in our model? So we will fix the weights. So now there will not be integer weights, because if you want to do smooth analysis, you have to normalize the problem. Otherwise, it doesn't make much sense. So we will normalize the problem by supposing that the weights are in -1, 1. So you have fixed some weights in -1, 1 of your graph, and you will perturb these weights by adding Gaussian noise if parameters 1 over to get the weights that you want. Okay, so our main theorem says that in this model, there is an algorithm that solves discounted and mean payoff games in polynomial time with high probability. Okay, so it doesn't matter. Well, there is a variant for discounted, variant for mean payoff, right? In this model with randomized weights. And what do I mean by high probability? Well, the probability can be as high as you want in some sense. So if you fix epsilon greater than 0, then you get this many iterations for ln epsilon -1 to solve the game with probability at least 1 minus epsilon. So for instance, if you want to solve the games with probability 1 minus 1 over n, then here this will be n. So this is poly n. Okay. So high probability means 1 minus 1 over n in reality. So as your graph gets bigger, your probability actually gets closer to 1. So it's not like high probability meaning 0.8, it's 1 minus 1 over n. Okay, and there is like an assumption that we have in the paper is that the underlying graph has some kind of a special structure. So I will explain this. Okay, and furthermore, our algorithm is a variant of a policy iteration method, one of these methods that we use. And our result is even a little bit stronger. So we prove that this is still true if you perturb the weights by any independent variables that are absolutely continuous have bounded densities. Density is bounded by this and variance bounded by this thing, which the Gaussian noise satisfies, but you know, if you like the uniform noise on some small interval, then that's also fine in this. Okay. So let me tell you something about the reality it works, right? So there were a few papers about randomized games, but not that many. I would say, surprisingly, not many. So there was this paper by Alain Benjamin and Gobert when they analyzed random games by under very symmetric distribution. So they had a distribution that's of the ways that they suppose is so-called flip invariant and showed that such programs can be solved in polynomial time on average. But this is like a very, very symmetric distribution of the weights. That, you know, somehow when you like flip the edges of the graph, then somehow it doesn't change. And things like that. So this is like very far from smooth setting, right? Smooth setting. So there's a paper by Mathieu and Wilson where they studied one player case. What happens randomly when you pick the weights from some random distribution, and you know there is like a very nice probabilistic analysis of what happens to the length of the cycles and stuff like this. And they say that they were motivated by the fact that they wanted to prove that some algorithm is efficient randomly, but they didn't manage. So the paper is about probability. So in some kind of opposite direction, there is a paper by John Gobert, Katz, and myself, in which we studied the value iteration, and we propose a condition number for value iteration, right? So we saw that the value iteration is like the polynomial, right? But in the paper, we saw that actually there is like a condition number. So the value iteration takes a long time only if this condition number is high. So if the condition number is low, then it's efficient, right? But in the paper, there is no proof that the condition number is low, right? Like the paper just says, you know, intuitively, it could be low. Experiments suggest that it may be low, you know, but there is no proof that it's actually low. And finally, there was a paper by Boris Basuni, Gurvich, Mackinnon, and McKay in 2011, where they claimed that they have the smooth analysis result for this mean-payoff games. And well, so they published a conference paper on this, and then they realized that the proof doesn't work. So then they later retracted the claim in the journal version of the paper, where they, you know, explain nicely where the mistake was, and you know they say, well, now we don't know how to do it and stuff like this. So you know, with Bruno, we managed to let's say re-establish the claim. Okay. So now I want to maybe explain maybe quickly. I don't know if you want to sit here for much longer.
Yeah.
Sorry?
Yeah, maybe not.
I think it's enough. Yeah. Okay. So I just wanted to explain you a little bit about the ideas of the proof. Okay. So to start, we can think about one player case. So there is this idea that somehow started our thinking about this, is that what should happen in the one player case? So you imagine a graph, and imagine it's a directed click, and you want to find the cycle with maximal weights. And you pick the weights at random. Okay, so if you are on a click, so there is like an exponential number of cycles, right? That you can do. However, if you run the experiments, for instance, then you can see that when you look at the optimal cycle and the second best cycle, the gap between them is actually big. Okay, so this is in this proposition. So suppose that my weights are uniform. Let's just think by this situation. So my proposition is that with probability at this 1 minus 1 over n, so with high probability, the difference between the mean weight of the optimal cycle and the second best cycle is large, at least this quantity.
Probability is for intrinsic weights. Yes.
Yes. Okay. So now let's see that this is really large, right? Because you have at least this many cycles, exponential number. So since you have this many cycles, and every single cycle has a mean weight between this and this, right? Because this is how I define the weights, right? So by the pigeonhole principle, right? I mean, there must be cycles that are extremely close to each other, right? So are this close to each other. 1 over n factorial. But the proposition tells you that the optimum and the second best is not n factorial, it's n to the 4th. Okay? So now the question is, well, how can we prove such a thing, right? That the optimum is so much higher from the second best. So our inspiration came from the optimal assignment problem. So in the optimal assignment problem, what we have like a bipartite graph and the weights on the edges, and you want to find the assignment from one side to the other side that minimizes the sum of the edges. So we want to find the matching with minimal weight, right? So this is known as the optimal assignment. Okay, and this has a probabilistic version. And you say, okay, so I take my bipartite graph, right? And I suppose it's like a bipartite clique, and by n, I take my weights from 0, 1 uniformly. So this is known as the random optimal assignment problem. And it turns out that this probabilistic model has been studied for a very long time. Like it goes to World Cup in 79, but actually there were some even earlier papers that were trying to do some experiments, but World Cup did some math there. And it turns out that this is a very interesting model for probabilists. So for instance, they were asking questions, let's say, well, what's the expected value of the optimal assignment in this model, right? And it took people years to prove. And of course, it's like p squared over 6 or something like this, right? Because of course, p has to appear. How could it not, right? So it's like pi over 6. So there are a lot of papers about this particular model. And in particular, there is this theorem by Fries and Sorkin, where they analyze a very similar question. Well, they say that for large n, the expected gap between the value of the best assignment and the second best assignment is at least 1 over 2n squared. And again, let us look at this thing. How many assignments do we have? Well, n factorial. We have n factorial assignments. They have values between 0 and n, right? So obviously, there will be assignments, a lot of them that are very close to each other. But the optimal one is far from the rest. So the optimal one is somehow isolated from them. Okay, and they have a very nice technique, but it's a little bit complicated technique based on linear programming when they analyze the so-called reduced cost at optimum condition on the optimal basis. So it's a very nice technique, but it's a little bit technical. So the second bit is or rather the second source of inspiration is the isolation lemma, which is like a little bit similar, but discrete version. So in the isolation lemma, you have some n objects and some family of subsets of these objects. So your family can have exponentially many sets inside. Right? And now you say that, well, if I have a set in my family, then the weight of this set is the sum of the weight of the objects in the set. And each object has weight at random from 1 to big N. And then there is this isolation lemma saying that with probability at least 1 minus n over n, the set with minimum weight is unique in your collection. But there is nothing about the cardinality of the collection, right? So you have like a exponential collection of the sets, like each of them has weight. And suddenly you say that, well, with high probability, the set with smallest weight is unique, no matter what your collection was at the beginning.
So you can take weights uniformly from an interval with, let's say, n squared points, right? So you can think, right?
The capital N is not square.
Right, so this capital N is like the precision with which you need to know the weights
Mhm.
in order to distinguish the minimum weight object from the
maximum.
maximum.
Okay.
Now, but there's a reason why this one works. It's not even work for one player case, because the one was for the two player case. For a reason, right? Because it's kind of min-max. I remember we thought about it,
Yeah. So
right? Because somehow, like, I think that's, doesn't this actually give the previous result, or maybe it doesn't? But
I shouldn't, right? I mean,
it shouldn't, but maybe it does. So right, so the family, now suppose that N is the number of edges in the graph,
yeah.
and I'll take your family to be a set of matchings.
Okay.
Right.
Okay, good.
Take your family to be a set of matchings. Now, now you take all the weights to be between 0 and 1, which is what we're saying, but now let's divide 0 and 1 into
Okay, yeah, sure.
capital N intervals, which is the same, right?
Let's say, yeah.
Now, then I choose just one side of each interval. Now,
Yeah.
with high probability,
Yeah. So you have the
the
unique.
thing will be
Set,
unique,
yeah.
but if it's unique, it's the only guy that has that value, so that means that the next one, the next highest. Right? So the next highest matching has
Interesting.
a weight that is at least 1/n bigger than the previous one. But capital N can be chosen, as you can see, to be like little n squared. And so kind of, actually, I think we just proved the previous.
Well, I'm sure about this discretization business, right? Because I'm still the weights that are uniform, right?
Yeah, very good.
Right.
The uniform weights certain also have some capital.
Yeah.
Yeah, but so somehow we have to go from uniqueness to the fact that the gap is large.
Their sums should also have some capital.
Because here, but that's the result of the limit, right?
Here it's just uniqueness, right?
The
Because
percentage is the sum of the
Okay,
weights.
because here the weights are not just the random weights of the edges, they're also the sum. The weight of a set is the sum of weights of the elements.
Yes.
And that,
That's also
are separated because the weights themselves are random definitions of itself.
Yeah, that's okay, but if you're thinking like n squared random weights, uniform weights in some interval, right? So there will be some separation, but it's not uniform. Like I can guarantee like with 99% probability that they won't be in the same.
They themselves won't be, but what if a subset of them is sum up to a number that is close to, that is not equal to, but close to the sum of another subset?
That will happen, of course, if you want to show that the minimum, but the minimum is this one.
Right. So we only care about that one sum.
Yeah. So I think that this actually shows the other theorem.
think so. Wow. Okay.
So the thing is that, I don't know, somehow we looked at the other theorem before, but.
Yes,
then
yes, I know, I know.
Then it's like, oh, this is just the isolation lemma. And then we thought of this, okay, and we now apply the isolation lemma to the game space, and then we can't, and there's a reason why we can't, and I hope you have a slide about that. Because otherwise it's true, like somehow. I mean, in the other paper, they prove a lot of other things, right? So it's not like.
Of course, yeah. So this is like like lemma 5. It was. I found it by like pure random chance that because there is so many papers on this, that there are like survey papers on this, and so I was reading like survey paper to say, and and once there is like this sentence in the survey paper. By the way, Fries and Sorkin proved that there is a large gap. I was like, wow, that's exactly what I want. Yes.
It's funny because so we found this other paper before. And then at some point, we were thinking of the isolation lemma to me, though this should be simplifying like a lot. But then what happens is that the isolation lemma does not work, so there's a reason we have it written in the paragraph. So why does the isolation lemma doesn't work on games? But then the other technique, which we by chance found before, can be adapted with
Exactly.
tricks.
Yeah, I didn't. Yeah, I actually don't have like a slide to explain a little bit about. Yeah, yes, indeed. There is like an idea of making this proof with isolation lemma that could work, but it doesn't. But yeah, I don't have the slide. But how somehow we mix these two things is by saying that, okay, this previous thing is very nice, but has a complicated proof, a bit technical and stuff, while this thing has a clever and short. So we will use the short and clever combined with the nice from the previous ones, and that will give us the thing. Okay, so that's the proof. Okay, but this thing has short and clever proof. So let me give you a short and clever proof for one player case. Okay, just to show you how nice it is. So we will say, okay, so we are in this one player situation. You have weights and random on the clip, right? And you want to find the cycle. Okay, so now we will do the following clever thing. So for for every edge, I will define a random variable, yij, and I define it like this. So I parameterize this edge by x. So instead of looking at my fixed weight, I will look at this as a parameter. And I will see what happens when all of the other weights are fixed and only my parameter varies. Okay? And this is how I define my random variable. So I will take the infimum of all x's such that this edge is not in the optimal cycle when I replace the weight of the edge by x. So I keep all of the other edges fixed. I replace the edge of ij by x. And I say, well, my y of ij is the infimum of all x's such that the edge is not in the optimal cycle. Okay?
The range of x is.
Because it's so amazing.
Oh, amazing.
So it's a maximizing game, right?
I think it's here on the slide I have minimizer, right? Yeah, here on in this part I have minimizer. Sorry. So this is for the minimizer.
So it makes it isn't the
No, but then I think you are maximum.
This is not me.
Right, so,
So
oh, no, I see. So you take the smallest x, just at the edge.
no, this is not in the optimal cycle. So imagine if your weight is very, very high, what should happen? Well, if it's sufficiently high, they will for sure not be in the optimal cycle because you're on a click. You can avoid it. Right? So now you take infimum of all of such x's, right? So you have this kind of a threshold, such that when you are above this threshold, you don't want the edge to be in the optimal cycle. Okay. So this is the threshold variable. But now we can think of, okay, what happens when I go below this threshold in the one player case? Well, that by definition, it means that you are in the optimal cycle. So this is like a strict threshold, right? So this is actually in the one player case, it's like a strict threshold because between above you are not in optimal cycle, below you are in the optimal. If you think about what happens when you just parameterize one edge, there will be a threshold number. When above you don't want it in cycle, below you want it in cycle. And this is this variable yij. But now here is the clever observation about this variable. This variable does not depend on the weight of the edge ij. Just by definition, right? Because it only depends on the other guys. Right? So it is independent on Rij. But since it's independent on Rij, what's the probability that Rij is close to it? Well, it's small because from the perspective of Rij, this is a constant. Right? So it's like saying, well, what's the probability that my uniform Rij is close to a constant? Well, it's the length of this interval times phi. Okay, that's the more formal proof with when you condition, right? You condition on R minus Ij, so now Y is a constant. And so the probability is 2 alpha. Where alpha is the length of the interval, right?
Yeah, so phi is the.
Yeah.
The sample. No, you don't need phi, you need 1/5. 1/5 is the length of the.
No, because this is an interval of length 1/2 phi, right? 1/5. Right, so you multiply by phi to get 1. Something like this. I hope I didn't.
Since well, very tiny, you could be unlucky that all of it's right, sorry, y idea is right in the middle of the interval. But then, you know, if alpha is very tiny.
Yes, I hope it's roughly correct. Okay, so that's the trick. So you are far, right? So now, well, you have the union bound, right? So by the union bound, with high probability, everybody is far away from the threshold, from their threshold. Every edge is far away from their threshold, right? But what this means for your optimal cycle? Okay, so suppose that this holds, which holds with high probability, as we have just shown, right? So let's see the cycle that is not optimal. So since your cycle is not optimal, so it contains an edge that is not in the optimal cycle. Right? Of course. So for this edge, Rij is by definition higher than the threshold. So by the property, it is very much higher than the threshold. Right? So now if you take this weight and you decrease it by this quantity, then the optimal cycle cannot change. Right? Because for every value above this threshold, this edge is not there, and this edge is not there. So by decreasing it, I didn't change the value of the optimal cycle, so it's still the same. But what does it mean? Well, that means that the mean way of my cycle, because it's the edge of the cycle C, right, that I'm changing. So it means that the mean weight of this is higher than the mean weight of my cycle, but at least this quantity, right? It's 1 and higher because it's mean. I change only one edge and I divide by. Okay. So that's a very clever trick, right? You introduce some threshold variables. You say, well, my threshold variables are independent of Rij. So by union bound, everybody is far away from the threshold. And it actually tells you that your optimal cycle has to be far from the second best. Okay, so one player case is very nice, right? And actually in this paper by Barros and al. From 2011, they have like more complicated proof, but if you look at the paper, basically they reach kind of the same conclusion, right? I mean, it's not written very precise because it's just a conference paper. But if you develop what they say, they basically had the kind of similar argument that could work for the one-player case. Okay, and then they said in this paper, they say, well, you know, so this kind of works in the one-player case. So they say, well, you know, so in the two-player case, it's like the same. Similar, you know, you will condition on one player and on the optimal policy of one player on something like this. And they say that then that if you take a mean-payoff game now with two players and you truncate, you take random weights and you try and truncate them, then somehow the optimal policies of the players do not change, which is like very similar to the previous one, right? In the previous case, we said the optimal cycle is far away from the second cycle, right? So if you approximate the weights, the optimal cycle will be the same, right? because the gap is large. So after some approximation, it's still big, right? So then they said that this should be true in the two-player case, basically. That you cut a little bit the random weights and the optimal policies do not change. This is something what they try to argue in the paper. However, there is like a big problem in this paper that the proof was wrong, right? And there is many technical issues here. Like for instance, in the previous case, we had the uniqueness of optimal cycle, which was clear because our cycles are different with the one player and stuff. But here, optimal policies may not be unique even if your payoffs are random, because you always can have like multiple ways of reaching a cycle or stuff like this. So arguing that, you know, cycles and the policies and stuff like this doesn't change. For mean-payoff games, it's really hard because you will always find a weird counterexample where you just perturb slightly one edge and somehow this changes the policy of one player, but the other player doesn't want to change it. Really, all kinds of weird behavior can happen. So what we did with Bruno is we did not prove or reprove this claim. We will only prove a weaker, more precise version of this claim. So in order to prove this weaker, more precise version, we somehow use this notion of the Blackwell bias. Okay, so here is just a slide about the assumption that we have. So our proof kind of, for now at least, works on the assumption that your graph is ergodic. So ergodic graph is a graph in which, for all choices of payoffs, the value is the same on all coordinates. So an example of this graph is bipartite clip, directed bipartite graph, complete bipartite graph, right? So if you are on a directed bipartite graph, then the value will not depend on your initial position because you can always go to the guy who gives you the best value. So it's somehow the value doesn't change when you change the starting position, okay? So this is a typical talk about this ergodic graph because it gives you a nice model, because you know you take payoffs at random and however you choose them, you know that the value is the same on all coordinates, right? So this is a very nice feature of this random. Yes, only in the mean payoff setting. So, but you know, we will prove that the discounted setting on these graphs also works. Okay. But this notion is defined for mean payoff setting. But you know, complete bipartite directed graph, I would say, probably the most reasonable model, right? I would argue that, you know, that's the first model that you should look at if you want random games. And also these graphs are somehow representative for the difficulty of the problem, because solving mean payoff games on this complete bipartite graph is as hard as solving all mean payoff games. So it's like representative. But you know, it's represent, but you know, this works under polynomial time reductions, but it doesn't mean that it's smoothed polynomial reductions. So you cannot, from our result, immediately get it for all graphs, right? So maybe there is something more to be done to make it on all graphs, but I think that the ergodic model is already very, very meaningful and very interesting also. Okay. So we will use this kind of graphs, and on this graph, on these ergodic graphs, we can prove a very nice property. One can prove a very nice property that the Blackwell bias satisfies this equation that is called the ergodic equation. So the Blackwell bias is like an invariant half line of your operator. So when you apply Shapley operator on the Blackwell bias, you don't get Blackwell bias as a fixed point, but you get the Blackwell bias plus the value. So it adds the value at every direction. Okay, so this is the property of this Blackwell bias. Okay. And this somehow allows you also to retrieve this property that we had for discounted gains. So for discounted gains, we said, well, if you want to find optimal policies, what do you do? We said you look at the value and you take the edges that achieve the max and the min. So now what we say is that, okay, you can do the same in the mean-payoff case by looking at this ergodic equation. So if you have a solution to the ergodic equation, so now the solution is the value plus the bias, and a player follows maxima or minima in this ergodic equation, then their policy is optimal. And maybe we can see just why this is the case. So suppose that max uses a policy sigma that achieves the maxima in this equation. So since you have the solution to this ergodic equation, so any edge in this graph will satisfy this inequality. Right? So once again, lambda plus ui is mean. So of course, every edge, so this is higher than every edge here. And here I defined the policy such that this is an equality. So lambda plus ui is greater than rij plus uj for every single edge of my graph.
Smaller if it's a minimum. Now I'm looking at minimums. We switch from minimum.
I switched something, right? It should be for max. Wait. Sorry, of course I am talking nonsense. This is minimum, so this is smaller than everybody. This thing is smaller than everybody. It's always making right? It's always confusing. This is smaller than everybody, and this is equal to for max. So this is also smaller than Rij plus J. Okay, now we arrive. Okay, so we have this inequality for every single edge of my graph. So what happens on a cycle? Well, when I look at the cycle, I can just add these inequalities, and the U part will simplify because we are on a cycle.
I mean, you leave Rij on one side, and you have lambda plus ui minus uj on the other. Right? And now, what's the mean weight of a cycle? It's just the sum of all these Rij's. But on the left, the sum telescopes. So also you use the square. And you get just the length of the cycle times gamma tilde. If you divide by the length of the cycle, that's just gamma.
Exactly.
So the mean weight of a cycle is at least gamma tilde. And by the same reasoning is at most gamma tilde.
Right. So if you have a solution to this ergodic equation, and Blackwell bias is one such solution, then you have a pair of optimal policies, kind of similar to what happened in the Shapley, in the discounted case with Shapley. Okay, so this is a nice property of this ergodic games. Okay, good. So but here there are more problems, right? Because in the discounted case, we said, well, a policy is optimal if and only if it satisfies this. But here, this is no longer the case. Actually, this ergodic equation can have many different solutions that give you different policies, which are all optimal, but not the same. And also you can have optimal policies that are not coming from this equation in any way. So all things can happen, right? So it's really complicated. However, if you have a solution, then you have a policy. And there is an interesting theorem by Akion, Gobert, and Oshar, who said that for generic weights if your graph has generic weights, then actually this bias, this ergodic equation, will have one solution up to adding a constant to every coordinate system. Okay, so now we say that the Blackwell bias is always a solution, but if the weights are generic, it's the unique solution up to trivial transformation. Okay, so now this gives us some sort of unicity for these games, right? So we said that in these mean-payoff games, you know, you can have multiple policies and stuff like this, but this object is generically unique. So you have some kind of a canonical notion of a solution that is unique if the weights are generic, right? So in our paper, we need slightly stronger statement. So we not only, but this is basically based on these techniques from this previous paper. So we proved that generically what happens to the way to these games is that you have a unique solution to the ergodic equation, and also the maxima and minima are achieved unique. So we have unique policies coming from this ergodic equation. And these policies have to be Blackwell optimal policies because Blackwell bias is a solution. Okay, so in other words, generically speaking, a game has a unique pair of Blackwell optimal policies. Okay, and this unique pair of Blackwell optimal policies is characterized by this ergodic equation. So this gives us a unicity. So instead of finding some policies, we can say, okay, let us analyze the Blackwell optimal policies. They will be generic. Okay. So now, as in the one-player case, we want to measure some kind of a difference between two things, right? So in the one-player case, we measure the distance between the cycle and the second best cycle. So here we measure this. So what is this? This thing looks at the ergodic equation and says, okay, so maximum and maxima and minima are achieved unique. Okay, so now we will measure the gap between the edge that achieves the maximum and the second best edge. And we will measure the gap between the edge that achieves minimum and the second best edge. And beta is the minimum of all of these gaps. So what is the smallest gap between the maximizing edge and the second best edge in this algebraic equation? Okay. And the motivation for this quantity really comes from this paper by Fries and Sorkin, because in the one-player case, you can write the one-player case as a linear program, and in this linear program, this is exactly the reduced cost at optimum, exactly like in the optimal assignment. So this is like a two-player generalization of what Fries and Sorkin did in optimal assignment. So this is this quantity beta. And this quantity behaves a little bit similar to this quantity that we studied before. So in the sense that that beta measures what will happen if one player deviates. So if maximizing player uses the Blackwell optimal policy and minimizing player uses a policy that is not the best response, then this beta will measure how much they lose. Okay, and the argument is very similar to what we have seen in the one-player case, because you look again at this equation, right? So since this tau is not the best response, there is like a strict inequality on some edge that minimizer uses. So in this inequality, you can plug in beta by the definition, because beta is the smallest gap. So the gap is at least beta. So you add these inequalities, you divide by, and you obtain on one side lambda plus beta over n. Okay. So this gap in this equation measures how much you lose if you deviate from the optimum. But you know, you have to really carefully choose the words. So one guy uses the Blackwell optimal policies, and the other guy uses the policy that is not the best response to this Blackwell optimal policy. Then they lose exactly this, at least this quantity. So it's much more complicated than in the one-player case, but it's similar, right? But it's similar. Okay. So this is what this beta measures, and then so we want to say that this beta parameter is large. Right, exactly as in the one-player case. So so here you have the definition of the threshold variable that will achieve this for you. So that's the definition, you know, as you can see, it takes a few lines, right? But so the definition of the threshold is there is a bias such that the edge does not achieve the maximum in the ergodic equation of the mean payoff gain with RIJ plus by x. So again, the same thing, you take an edge parameterized by x, and this is the threshold. So you have to carefully choose the words, right? But if you carefully choose the word, well, as previously, this doesn't depend on Rij because it's a threshold when you parameterize. So this you have this, right? And then you choose and then you prove that, you know, because we chose this variable in this particular set of words, this actually measures the gap, measures this parameter beta. So there is a proof here. Okay. So as a corollary, we get that with high probability, this gap in this ergodic equation is high. Okay, so this is the analog, probabilistic analog of what happens in one player case. There is only one problem with this. I don't know how to get from this to an algorithm immediately. So in order to do that, we studied a little bit more what happens with this parameter beta. So as I told you, in this generic case, the Blackwell optimal policies are unique. So it turns out that this parameter beta measures also the Blackwell threshold. So we said yesterday that this Blackwell threshold is a discount factor above which every optimal policy becomes Blackwell optimal. So now we have uniqueness of the Blackwell optimal policies, right? So above Blackwell threshold, these policies are optimal. But now, how big is the Blackwell threshold? So we have seen the estimate with 2 to the n, w to the n, or something. But this turns out that if you look at this ergodic equation, and you have this gap between the maxima and the minima, beta, then since Blackwell bias comes from this development of the value, this beta tells you that the Blackwell threshold cannot be too high. The higher the beta is, the lower the Blackwell threshold. Okay.
If the Blackwell threshold is large, then the second order term is not relevant. So that means gamma star is 2 close to 1, and so the second order term is not relevant. So the bias is not relevant. So that's logic.
No, the good thing here is that for random game, the threshold is small, meaning it's bounded away
from 1. Yeah, that's what we want to prove,
so
right?
if you choose random weights on game, the discount factor after which the truth is revealed is actually bounded away from 1.
Yeah.
And there we have algorithms. So I have algorithms exactly getting this gap.
Exactly. Right. So this is what's written here. So we introduce this correlation number, which is defined using the parameter beta, the normalized parameter. Okay. And we say, and we prove that if the weights are generic and you take gamma higher than this quantity, then you are already higher than the Blackwell threshold. Okay. So what does it mean? It means that if this quantity is small, right, then you do not need a large discount factor to find Blackwell optimal policies. Okay. But we have already seen that, you know, high probability the beta is high. So if high probability, this field is small. So this is far away from 1, right? So that's written when you do the computation. Probability that delta is higher than this quantity is at most exciting.
Probability that the condition number is bigger than the number of edges, let's say roughly by epsilon, is at most
Epsilon.
There's this phi also.
And there is phi, right? Because it should, right?
The gap.
Which is the gap, right? So if the phi is
phi, so the interval is -1 over phi and 1 over phi. So
yeah.
if this interval,
so yeah, so if phi is very, very large, then your interval is very, very small, and So this probability becomes higher, right?
So if your random interval where your weight comes from is like at least one over Paulian large, then this condition number is at most polynomial.
M is the number of edges.
M is the edges, yes.
This is the general state, not about ergodic graph.
Yes, it's an ergodic.
I mean, there are ergodic graphs that are not complete graphs, so there's sparse ergodic graphs.
Yeah, they can be fast, yeah.
Yeah.
Well, actually,
So a graph is ergodic,
Yeah.
it's essentially if no player can get the other player stuck on some subgraph.
mhm.
It's sometimes strong connectivity notion for two players.
Yeah, so this, you know, this is for ergodic graphs because we measure what happens to this ergodic equation, but you know, in this ergodic equation, when you plug in random weights, so it's good to have an ergodic graph so that you know that your ergodic equation has solution, right? So this is much easier to work in this case, right? So that's that's basically the way that we prove the theorem. So we introduce this parameter beta. We show that it actually kind of measures somewhat similar quantity to what happened in one-player case. But then we say, well, okay, maybe this is not enough to do an algorithm. But this beta has this second property that it also measures the Blackwell threshold. Okay. But now, well, the corollary of this is random games have low Blackwell threshold with high probability. So for every epsilon greater than 0, the probability that the Blackwell threshold is higher than this thingy is at most epsilon. But this suggests us an algorithm, right? You just want to solve a discounted game with this threshold and get the Blackwell policies, Blackwell optimal policies. So if you want to do that in a like systemic manner, because you don't know this quantity, right? Like when you are at the beginning, you are given a random game. So, maybe you could guess what should be the Blackwell threshold or have some estimate, but you can also do a thing like this, which we proposed in the paper. So you start with gamma equal 1/2. And you compute the optimal policies using policy iteration. So, it's strongly polynomial for fixed gamma, right? Okay. So then check if these policies happen to be Blackwell optimal in your entire game. If they are Blackwell optimal, you won. If they are not Blackwell optimal, well, then, up the gamma, right? So now it's 1 minus 1 over 4. Then it's 1 over 1, 1 minus 1 over 8, 1 minus 1 over 16, and so on, right? You up the gamma, you solve, check if the policies are Blackwell optimal, and repeat. And at some point, this procedure will converge for any game, because any game has a finite Blackwell threshold, so this will converge. But if you plug it on a random game, then what will happen? Well, the Blackwell threshold should be low with high probability. So the number of updates that you do to the gamma is low. It's like a logarithm of this. But the main point is that at every gamma, the number of iteration of your policy iteration is polynomial in, like pseudo-polynomial in gamma. But gamma is polynomial in the input. So now this is a polynomial time algorithm, right? Because it never reaches high gamma. Well, otherwise it never. With high probability, it doesn't reach high gamma. So with high probability, this kind of algorithm stops in polynomial time. So this is the formal version, right? So for every epsilon in the halves, we need this many iterations with probability at least 1 minus epsilon. So if we want probability 1 minus 1 over n, so this is polynomial in m, and phi. Okay, and well, that's it. That you basically the important bit is that at every stage, at every discount factor, you use an algorithm which is pseudo polynomial in the discount factor, but fortunately, this discount factor will be polynomially bounded in the range. Okay, so now if we want to go to discounted games, well, we do the same. You just say, well, if you have some target discount that you want to reach, you just update, but never cross this target discount. And this will work because if it so happens that your target discount is very high, then it's probably higher than the Blackwell threshold, right? So when your update reaches the Blackwell threshold, it already finds the Blackwell optimal policies, so they will be optimal for your target discount. So we can find, so if somebody gives you very high discount, it's very probable that you will find the same policies on a much lower discount. And it's the same. Okay, and the last slide is about the so-called Oracle model. That was studied in this previous paper. So the thing here is that, okay, you have this mathematical model in which you take payoffs at random, but you cannot really represent random payoffs on a Turing machine, right? So people also study what they call an oracle model, in which you have an oracle that spits you the random bits bit by bit. So you can ask your machine for the next bit of your random weight, and then you want to solve it in this model, solve the game in this model. Okay, and how do you solve it? Well, assuming we do some kind of similar things to what Boros et al. Did. So we say, okay, if we truncate the random weights to this log n bits, then with high probability, this Blackwell optimal policies will not change. Because again, the beta will be still like large. If you truncate, if we approximate the weights, so you can run the same algorithm. You can run the same algorithm, but now at each step you have to ask the oracle for more and more bits. So you update both the discount factor and how many bits do you ask from your oracle, and I think at this point this is fine. But okay, I just wanted to mention this because Boros et al. Used this model as an oracle. So that was really the last slide. So this is now the kind of questions that are for future, right? So first of all, well, can we do this for arbitrary non-ergodic graphs? Second question is, can we get the same result for some standard policy iteration, right? So I showed you this graph for policy iteration method, but it's not the policy that we proposed here, right? So we proposed some kind of a method that works, but it's not the kind of method that people use, because people are interested in having like a policy iteration rule and tell me that this rule is fast, right? Well, we say, you will increase the discount factor and it will be fast, right? So that's the second question. But the first question is about value iteration, right? So I told you that there is some condition number for this value iteration, but we don't know if it's bounded, nicely bounded for random games. And there is also this class of stochastic mean-payoff games. So maybe we can prove something for that, or two other problems in this TFFD class. Okay, so that really was the last slide. Okay, thanks. So,
what is the review?
You need the potential one. So imagine that you have a 16-bit voting of a grant, and assume that there's this promise that if there's each node in the graph, get an economic edge, and associated with this each node there's a potential, a value. And the value must always, let's say, increase or decrease. And now finally,
Any iteration algorithm.
right, any iteration algorithm can just run, right? But it runs exponential, but now find do it fast. Or find the growth like the graph is aligned, the potential is increasing. And of course, like this problem is here because I don't know. So let's say if the graph is ergodic, the value is the same everywhere, so you can stop when the value is the same everywhere. And so it could be the difference between the smallest and the highest value and the value vector. Once it's zero, you won. So this problem is here. Consider right now. So you do value iteration, for example, Some UE OPL algorithm, which maybe. Yeah, that's one of the reasons. Classes where this thing is. But I mean, it's not known whether this is an NP interest. That's actually a very natural question. Right, because so the point is that it's unique, right, so you can even take like the promise. I promise you that it's unique, that the graph is aligned, and solve it. No. But you know, and the value, the secret that they the notes. With the promise, without the promise. Right.
Okay, thank you.